Archimedes principle. So we have seen that certain objects will sink in a fluid, but certain other kind of object will be floating. For example, you will see a ship will be floating on water, but if you put a nail, the nail will sink. Now interesting, for example, if I try to draw, this is, let's say this is the water surface, this is the water surface here. I put a boat here now. I'll keep a boat. The boat is this boat is not sinking, but if you see, this boat will be not, but the boat will not sink. If I draw a little, let me give it little shape over it. This boat is not going to sink. However, if I place a nail here, a solid nail, this is definitely going to sink. This is definitely going to fall into the water, sink in the water. Now if someone want that this nail should not sink, what he or she can do is that you place a big paper here over this liquid, and then you put the nail. Then it will not sink. So what is happening here? The nail, which if you release normally will sink, but if you take the nail and put it on a big piece of paper, then the nail is not sinking. So what is happening here? To understand this, we must know what is Archimedes principle. This principle was first observed by Archimedes, and he also gave the famous word eureka. He was taking a bath, and when he came across this principle. So what is it? Let's see. So Archimedes principle states that when a body is partially or fully submerged in a fluid, it will experience an upward force known as buoyant force, whose magnitude would be equal to the weight of the liquid or fluid, displaced by the object. So in this case, the nail is not displacing much fluid. So the weight of that displaced fluid is so little to balance its counterweight. So its weight is mg here. The buoyant force is there, but is very, very little. In this case, what is happening is that for the boat, what we see for the boat is, look at the shape of the boat. Look at the shape of the boat. The boat is displacing so much water here. It is displacing so much water in this region. So as it is displacing so much water, so much liquid or fluid, so it is having necessary upward force called the buoyant force, which is up here. We denote it by U to counter its weight downward. So that is why it has been able to balance itself in the sea. Now look at the case of the nail. When you put it on a paper, so this is being the paper now. So this being the paper, so this being the paper now, the paper area is now quite a long area, much area. So it is now displacing quite a huge sum of fluid, and consequently what do we see? The magnitude of buoyant force is now good enough to balance the weight of the I'm drawing it, let me draw it straight only. I'm just so this is the U. This is the weight mg, and this is U. So it's been able to balance it, so it will not sink. In this case, it is definitely going to sink. Nail will sink. This is not going to sink anymore. So this principle was first observed by Archimedes. Now let us prove it mathematically. Let us prove this mathematically, that how it is possible. To understand this, to come to the proof, we will consider a container. We will consider a container here. Let's say this is any container. Which consists of some kind of fluid. We denote this fluid by some kind of fluid is present. We also have, now imagine we place a an object fully immersed inside. It can be any. I'm showing you a cube. It can be anything. It can be any kind of shape object. So it is at a depth of, let's say, x below the level of the liquid, and its own height is h. So the different forces that is acting, the side forces, there are forces acting on the side. There's a forces acting on this side also, but these two would be equal and opposite, so there is no question on it, because they are the same height, so they will cancel each other. What about the forces acting on the top? That is Ft, and the force acting at the bottom. They will not be same. They are at different depth. As we go more deep, we have seen the pressure increases. And so we start by considering consider an object of density. Here density is very important. Density of this object is sigma. Consider an object of density sigma cross-sectional area A, height h, is fully immersed in a fluid of density rho. It is at a depth of x from the level of the fluid. Then forces acting at the top and bottom surfaces of the object is, so what do you think we can write? F1 will be, F1 can be written as, in terms of pressure we can write this P, Ft would be equals to Pt into cross-sectional area, and pressure at the bottom Pb into area. But this one, pressure can be written as H rho g. So this one should be X rho g into area. Similarly, Pb can be written as total height, total depth. In this case would be x plus h into rho into g into a. So the net, F net in this case will be now if you go for the F net, if you see the F net, the difference between two forces, so it should be Fb, F bottom minus F top. So if I do this, I see that it would be x plus h into rho Ga minus x rho Ga. So you can clearly see x and x will get cancelled out. We will be having only h into a rho g, but the volume of the object, volume of the liquid, volume of the, not the object, volume of the liquid column as displaced by the object V equals to rho, no, not rho, it would be cross-sectional area A into H. So if we try to keep a tray here, we will see the liquid that will come out when you drop this object here, and if we try to collect this liquid on this small tray kept on the side, we will see the volume of this liquid placed on the small tray will be AH, which is this one. So now if you measure the weight of this liquid, how much it has displaced. If we measure this, we will see that F net, so F net is coming to be, F net, that is upward force, is coming to be as, I'll substitute it here, V rho g. This force is called the buoyant force. And is directed upward, or in another word we can say directed upward or normal to the it is denoted by the letter U. So U is V rho g. Remember, rho is the density of the liquid. Now if we consider the apparent weight, so what does the weight become? So if this is our object, so this is our object. So the buoyant force is directed up, and the weight of the liquid is directed down. So this is the weight of the object, and U is the buoyant force up. So the apparent weight of the object will be now actual weight minus the buoyant force. So the apparent weight, which we denoted by, let's say, W dash, will be the actual weight W minus the buoyant force. So this is mg minus V rho g, correct? So but mass, if the sigma is the density of the liquid, so sigma is the density of the object given as density mass by volume. So we can write mass as volume into sigma. So then we can write this as V sigma g minus V rho g. So taking these things common out, we can take the volume common out, g common out, we are left with V g common out, we are left with sigma minus rho. Little bit of more alteration, I will do it here. So W will be now, so from here to here you can do it, I will do it here. So W dash can be, if I take this, I will take multiply divide by sigma. So if I do this, I get here V sigma g is equal to 1 minus rho by sigma. What is this? Isn't this the weight of the liquid? Actual weight. So we can write this W 1 minus rho by sigma. So this ratio will now decide the law of flotation. This ratio is not going to decide the law of flotation, whether the object is going to float completely, whether it is going to sink or whether it is going to be completely sinking or partially sinking it. This thing will be decided by the law of flotation. Let's see what is law of flotation. So law of flotation. So law of flotation states, let's see. So if the weight of the object, if W is greater than the weight of the object W is greater than the buoyant force, then what will happen? If you look at the case, if this is greater than this, in that case what is going to happen? V sigma G will be greater than V rho G. So we can clearly see that sigma density of the object is greater than the density of the fluid. So the body sink in the fluid. Number 2, W equals to U. So the buoyant force is equal to weight of the liquid. Then we see V sigma G will be equals to V rho G. In this case, sigma will be equals to rho. What does this mean? This means, so I'll draw it here. In this case, I should draw pictures side by side to give you an idea what we are doing here. So in this case, if this is the same container, this is our object. So the object is here and this is the liquid. So this is rho sigma, sinked, completely sinking. Now if I say in this case, what will happen in this case? Let's see. So in this case, as there is no net upward force, the density both of them are equal, where it will lie? So this is the liquid and this is our object. So the object will be floating near the edge, near the level of the fluid. So we'll write it. So the body floats fully immersed. Finally, the last case, weight is less than the buoyant force. That means V sigma G is less than V rho G. So we will see the sigma is less than rho. As sigma is less than rho implies the body floats. The body floats in the liquid, in the fluid. So the case is, for example, a cork. Example of a cork, a rubber cork or a toy, plastic toy, which is floating on the surface. You can see this is some kind of rubber toy which is floating. Okay, so it is floating toy. plastic toy floating. Correct? So these are called the law of flotation. To understand this more properly, we'll consider the case of the, let's see one numerical to understand this more properly. Now there is also another case called the partially submerged. Let us see with an example of an iceberg. So this is an iceberg which is partially floating. Which is partially floating in sea. Density of iceberg is 900 kg per meter cube, and you know density of sea water is 1030 kg per meter cube. So what fraction of the iceberg is submerged? So what we see is that if this portion, if we can easily find out that how much portion. So if you use the law of flotation here, I am not giving any other size and all, that how much is the dimension, we are not going into that. So using law of flotation, what we can say, that the density of the weight of the ice that is floating weight of the ice will be equal to the weight of the liquid displaced. So if V dash is the weight of the ice, V is the weight of the ice, let's say V is the weight of the ice, V dash is the weight of the fluid displaced, so this would be volume. So rho G, we know rho G H. So if this much, I'm just keeping it here, if it is complete, it is partially floating. It's partially floating. As you can see, it's partially floating. If this is the complete H height, the amount which is under is X. Right? So that means this much of fluid has been displaced. Not fully. So rho G, so rho Gx will be equal to this has been removed. The volume of the ice will be rho G, let me name this H, So rho gh will be equals to, you are displacing this much volume, so sigma gx. So if you cancel this, from here, looking into the ratio rho by sigma, we can easily determine x by h. So here I have given rho to be 900. So 900 by 1030 is equal to x by h. So let's say if the height is given to you, that it is, let's say, around 1 meter or 1000 meter, it will be very big, 1000 meter. So we can easily find out how much it is. Let us see, if h equals to 1000 meter or 1 kilometer, so they are very big generally. So x is equal to 900 into 1000 divided by 1030. I am taking this almost equivalent to 1000 only. So you can see x is almost equivalent to 900 meter. It is less than that, almost equivalent to 900 meter. I am just taking this, you can further find it out. Almost equal 900 meter underneath, and only 100 meter which is above. Okay. So this is how we can easily determine how much is submerged and how much is floating. Let us take another example. This time we will see let us take another example. We have a tank here which has water and mercury. So up to this level is mercury, and up to this level is water. So this is water, this is mercury. We need to find, and also we have an object which is partially submerged in both of them. Partially submerged. Certain portion is inside. I think I should draw a little big way. So what I mean is that it is partially submerged. Some portion is inside the mercury and some portion is in the water. It's partially submerged. That's good. So we need to determine what is the fraction of this is inside the mercury. How much of is it inside the mercury? Let's say this is a cube of side, let's say 6 centimeter. Determine the portion, determine the fraction of the cube inside the mercury. Let's see how we do it. So what we see here, the logic here is this: there will be a buoyant force. Due to water. There will also be a buoyant force due to mercury. Which will be balancing the weight? The weight is, this is the weight. So what we can write? So we can write weight of the fluid, liquid, would be the buoyant force of water plus buoyant force of mercury. So what is the buoyant force of water? It would be the amount it is displaced. Let's say we say the x is, so this distance is 6. This distance is 6 given to us. That means, let's say this point is x. So this must be 6 minus x. So knowing this to fact, what we can do is, so the volume we know what it would be the area into height, area, cross-sectional area being same, it's a cube, so area into x ax, volume v rho g, so volume I am writing this as ax into density. Density is, okay, I did not give you the density. Let us say this is iron. This is made of iron, so that would also be needed. So I will give this iron. So density of iron is around 7 gram per centimeter cube. So it should be 7 into 10 to the power 3 kg per meter cube. This is also needed. So so it is in which liquid? It is in I think it is better that we take this one as x and this is 6 minus x. So this is x, this will be easier then. 6 minus x. So ax into a into 6 minus x, sorry. So we'll change it. A into it's a centimeter, so it should be 0.06 minus x into density of water, which we know as 10 to the power 3 into 10 gh, plus mercury would be area into 13.6, oh no, sorry, x, this is x, now there, into x into 13.6 into 10 to the power 3 into 10. So area, as it is a cube, its area would be 0.06 whole square. So 0.06 minus x into 10 to the power 4, let's say, plus 0.06 whole square. Why whole square? Because it's a cube, so side square. Then into x into 13.6 into 10 to the power 3, that will make this as 10 to the power 4. So knowing this, now what is the weight? The weight will be, the weight of the object will be, again we can write the weight as, mass can be written as density into, so sigma density, density into volume. So that is the volume, complete volume would be 6 square, 0.6 square, okay, yeah, and the volume into height, height is also 6 centimeter, so this would be 0.06 whole cube, into g. So we can write this as 7.77, let's say. So 7 into 10 to the power 3 into 10 into 0.06 whole cube is equal to 0.06 whole square into 0.06 minus x into 10 to the power 4 plus 0.06 whole square into 13.6 into 10 to the power 4. We can remove square from here, so it is left with 7 into 10 to the power 4. I think 10 to the power 4 can also be removed. 10 to the power this one, this and this can be removed. So I'm not going to write here anything like that. So we can write this as 7 into 0.06 is equal to 0.06 minus x, then again plus 13.6 into x. There will be one x here. Yeah, there is one x into x. So solving this, we can easily determine what is the value of. So let us do it. So we can see this 13.6. So this will give me 0.06 minus x plus 13.6x. That gives me 12.6. So 0.06 minus plus 12.6x. So this goes there, 7 6 are 42. So 0.42 is equal to 0.06 plus 12.6x. So if I solve this, so x will be giving me 0.42 minus 0.06 by 12.6. So this gives me 6. 0.36 divided by 12.6. If I am not mistaken, if my calculations is correct, then this value, if I divide it, I will be getting it. Let's see. I will be having a calculator here. Okay, so 0.3 clear 0.36 divided by 12.6 gives me around 0.02 or 0.03. So x comes out to be 0.03 meter. I write the answer here, 0.03 0.03 meter. So this is how you can determine when multiple substances are involved. Okay.